Today we're going to be talking about unstable nuclei and how it is they decay and what happens after they start. So it's worth defining first of all what an unstable nucleus is, and this is one that has too much energy in the nucleus or the wrong mix of particles. Now, what the wrong mix of particles is not something that we need to know at this stage. But isotopes of atoms that do this, and we need to know what an isotope is. It's a form of an element with a different mass number but the same atomic number. That's what makes it the element. They're called radioisotopes, radioactive isotopes in other words. And two of the most important starting points are the idea of radioactive decay being both random and spontaneous. So what random means is that if you look at a sample of a radioactive material, you cannot predict which nucleus is going to be the next one to decay. Or if you're looking at a particular nucleus, there is no way for you to predict when that nucleus is going to decay. There is a slight probability for every nucleus each second that it might decay. Spontaneous means that there's nothing you can do about speeding up or slowing down the rate of decay, no physical factors. So you can increase its temperature, you can decrease the temperature, you can apply pressure. None of this makes any difference. The rate of decay or the probability that something will decay is determined only by the nucleus itself. It is a specific number for every element. So if you have a sample of a radioisotope with n undecayed nuclei, how many of those nuclei will decay in a second? Well, usually because in any particular sample we have a large number of nuclei involved, we can use statistical techniques to describe this. We can assume that the rate of decay is proportional to the number of nuclei present. That is, the more nuclei we have, the more likely it is that one of them will decay. Now, the number of decays per second is called the isotope's activity, how radioactive it is. And this is measured, given the symbol A, and measured in a unit called becquerels, which is shortened to BQ like this. It is worth pointing out the difference between activity and count rate, because when we do the experiments, we tend to look at the count rate received from a source. And the count rate is really just the number of clicks that are received from a source along a line, whereas the activity is the total number of decays per second out in all directions from the actual sample sitting inside the sources that traditionally look like this. So the count rate is one particular line, whereas activity is in all directions, and so comes out as a sphere. What does the activity depend upon? Well, we've just said activity depends on the number of nuclei that are present. And so the activity is the decays per second, remember? So how many decays you get every second is proportional to the number of nuclei present. And this is called the decay constant. This is the probability that an individual nucleus will decay per second, and usually has units of per second, or it could be per day, per week, per year. It's given in a lot of different units depending on how quickly the radioisotope decays. And remember, this decay constant is a property of a particular radioisotope. So every single radioisotope has its own decay constant. A large value of this means that you'll have a high activity, as we can see here. So if our lambda value increases, our activity value is going to go up, so we'll get more decays per second. And the sample will decay quickly, because your n is going to go down as a result. So the greater the decay constant, the higher activity, and the number of undecayed nuclei you have goes down. This is a very important equation for being able to calculate the activity of a sample from the number of nuclei that you have. As long as you know the decay constant, you can figure out what the activity of a sample is going to be. Or, vice versa, if you have the decay constant, you can figure out how many nuclei you have from the activity. As time passes, the strength, if you like, the amount of particles coming out of a radioactive source, its decay rate, its activity decreases, like as shown in this graph here. So the rate of decay, that is our dn dt, remembering that that is equal to A, and it's the minus just tells you that it's decreasing. The rate of decay is going to go down. and therefore the number of decays per second goes down. However, we can measure what is called the half-life for an element in a sample, and we met this at GCSE. So looking at the graph, this kind of graph is the first way that we can use to measure the half-life. So if we find half the original activity, and our original activity at time equals 0 was 100, we go down to 50, we go across, and we go down, we find the half-life here being 8 days. Now, when you're doing this from a graph, it is a good idea to do it several times. You go down to 25 and down and take an average. Do as many times as you can and take an average. Because radioactivity is an entirely random process, we can only ever get an average value of the half-life because it will be slightly different every time we measure it. But if you have a large number of nuclei in your sample, it means that your decay equation is statistically valid. You will see this graph with other possibilities on the y-axis. So for example, instead of activity, it could be number of nuclei in the sample, because we know that activity is proportional to n. It could be the mass of the particular isotope that I've just given x here, because of course mass is going to be proportional to the number of nuclei, which is proportional to the activity. So these things are always, they're going to give you the same sort of relationship. And of course, you could have percentage of the X isotope, starting at 100% and dropping down from there. But of course, the maximum of that is 100. It is very important to know the definition of the half-life, and there are two possible definitions here. You can use the number of nuclei, so it's the average time, and average is very important here. It is the average time taken for half the original number of nuclei in a sample to decay, or you can use the activity. It is the average time, again, very importantly, taken for the activity to fall to 1/2 of its original value. So make sure that you have written this down somewhere and just learned it. These are the equations that control this graph, and as you can see, they're exponential equations, and they are exponentially decreasing equations because of the presence of this negative. Now, these, again, n is proportional to a, and a is proportional to n. So remember that these equations are basically interchangeable depending on what you have on your y-axis. And what are these telling us? So let's focus on the n equation for the moment. The n0 here is the original number of nuclei in the sample. So what they're saying is that the number of nuclei that are left is proportional to the original number that you had. And also to this. What we have up here is our decay constant. This t here represents the time since the decay began. So what this allows us to do is for any sample we know its activity or its number of nuclei right now, we can figure out what its original number of nuclei or activity was, as long as we know the time constant and the time since the beginning of the decay. So what can we actually do with these equations? So we'll use this activity equation on the bottom to do this. And we're going to take the natural logs of either side. So we have ln A is equal to ln A0. The natural log of E is 1, and so it just becomes minus lambda t. I'm going to rearrange that a little bit and say, okay, ln A is equal to minus lambda t plus ln A0. And this is in the form of y is equal to mx plus c. So if you are monitoring the activity of a sample over time, you can put time on your x-axis, ln A on your y-axis, and we would expect to get a line with a negative gradient, and with the intercept being ln A0. And that is exactly what we get. This graph is for ln n, it could just as easily be ln A. Your gradient is equal to the decay constant. So this is one of the ways that we have of actually finding the decay constant of a radioactive isotope that you're monitoring over time. The intercept up here will be equal to ln AO, so you can find the original activity of your sample by extrapolating back to the y-axis and finding the anti-log of that. You need to be comfortable working with natural logs, so make sure that you know how to take the natural logs of an equation like this. Let's have a look at some other interesting derivations that you can do with this. So, after one half-life, the t in our equation is equal to t a half. And let's just write our equation up here again, e to the power of minus lambda t. So that t is the time since the decay began. And after one half-life, it's equal to a half-life. That means that our AO is going to be equal to twice our A. So A is half AO. So that means that we could put A over AO, and that would be equal to a half. So we can take our equation up here, and we can say, okay, A over AO is equal to e to the power of minus lambda t. But we know that A over AO is equal to a half, so a half is equal to e to the power of minus lambda t. If we now log this, we would say, all right, ln a half is equal to minus lambda t. And ln a half is equal to minus 0.693 minus lambda t. So therefore, 0.693 equals lambda t. And so what you can do, and of course these are all t a half, because we said at the very beginning that this was valid when A over AO is equal to a half, and that happens at the half-life. What this means is that using this, you can find the half-life from the activity, or you can find the activity from the half-life. And that's a very important equation. It's sometimes written as t a half, and this is what it is in the data book, is equal to ln2 over lambda. Because minus 0.693 is ln a half, and 0.693 is therefore ln2. And so ln2 divided by lambda will give you t a half. This is an equation that is used a lot in exam questions. So they'll give you the half-life so that you can find the decay constant and put it into this equation up here, so that you can find the current activity of a sample when its original activity was blah. So that's interesting derivation number 1. Interesting derivation number 2, if you think after one half-life, we know that n is equal to n over 2. After 2 half-lives, we know that n is equal to NO over 4. And 3 half-lives, NO over 8, and so on. So we can see here that n is equal to NO over 2 to the power of n. You can figure out how many nuclei, or again, the activity, you know, its original activity, and you can multiply it by 1 over 2 to the power of n, where n is the number of half-lives. And this makes it very, very simple. The fraction that is left of nuclei or of activity is multiplied by a factor of 1 over 2 to the power of n of the original. Now, knowledge of half-lives is vital in many situations. So they're used in medicine, not these particular ones. Iodine 131 is used extensively in medicine, and that has a half-life of 8.1 days. They're used in radioactive dating, so uranium is often used in the dating of rocks, and carbon-14 is used in the dating of human archaeological sites. And if the environment has been contaminated by a nuclear accident, oftentimes cesium-137 is released in that case, and that has a half-life of 30.2 years. Remember, that is the time it takes to fall to half. So let's have a look at an example from the dating of rocks, geological dating. And oftentimes it's used using the decay of uranium-238 because it has a very long half-life, as you can see here. And it goes through a decay series ending up as lead. So if we assume that there was no lead in the rock when it was formed, and that all the atoms were uranium, then the ratio of the number of atoms of lead to the number of atoms of uranium could give us the age of the sample. Now, how does that work? So if we say, okay, the number of atoms of uranium, that's our N, is equal to the number of atoms, original atoms of uranium, which will be the current atoms of uranium, plus the atoms of lead that are in the sample right now. So that's our NO times e to the power of minus lambda t. Now you can find out what your lambda is from the half-life. So we can use ln2 over the half-life, and we would get a lambda of 5 times 10 to the minus 18 per second. So what do we do with this equation? Well, we're going to divide across by nu, and that will give us 1 is equal to 1 plus npb over nu on e to the power of minus lambda t. Now we already know that the ratio of lead to uranium is 0.7, so we can substitute that in there. 1 is equal to 1 plus 0.7 on e to the power of minus lambda t. We now divide our 1 by 1.7, and we get 0.588 is equal to e to the power of minus lambda t. And if we log both sides of that, we do ln 0.588, we get minus 0.531 is equal to minus lambda t. Obviously the minuses are going to disappear, and so we can substitute our lambda in here, and our t then will be equal to 0.531 divided by 5 times 10 to the minus 18, giving us 1.02 times 10 to the 17 seconds, which is 3.37 times 10 to the 9 years. And that is the age of our sample. What sort of exam questions can we expect to get? So let's have a look at some sample questions. We have phosphogypsum is a byproduct of the manufacture of fertilizer, slightly radioactive because of the presence of radium, and it has a half-life of 1600 years. Okay, that is the first piece of information that we need to keep an eye on. That's our half-life. It must be stored securely as long as the activity it contains is greater than 0.4 becquerels per gram. So this is something else we're going to keep an eye on. In a sample of 1 gram, so we don't have to worry about the number of grams, the activity is 1.3 becquerels. That's our A. Calculate the number of nuclei of radium in the sample. We want N. I find this labeling very easy because it allows you to see very quickly what you have and what you need. So we know we have A and we have N. We know we have an equation. A is equal to lambda N. So we need to find lambda, and we can do that because we have the half-life. So let's do that first. Lambda is equal to ln2 over t a half, giving us a lambda of 4.33 times 10 to the minus 4 per year. So in this situation, I've put in 1,600 years as the t a half, giving me a decay constant per year. You have to be very careful in using these equations, making sure that your time and your decay constant are in the same unit. Okay, if we now substitute this in here, our activity is 1.3 becquerels, and we have 4.33. Just keep that in your calculator, times 10 to the minus 4 times n, giving us an n of 3001 nuclei. That is rounded, but if you keep it in this number, this decay constant number in your calculator, you end up with 3001. Fairly straightforward for 3 marks, especially if you label all the quantities that you're given so that it's very clear what equations you should be using. Part 2 then says calculate the time in years it would take before the sample reached the permitted level of decay rate. Our permitted level was an activity of 0.4 becquerels. So we want to see how long does it take before it gets to 0.4 when its current, our AO, is 1.3. And we know our decay constant is 4.33 times 10 to the minus 4 per year. All taken from the first part of that question. This is, we can see we've got A, we've got AO, we've got lambda, and we want the time in years, so we're looking for that small t. And so we're going to use our equation A is equal to AO e to the power of minus lambda t. And we're going to go ahead and just go A over AO equals e to the power of minus lambda t. A over AO is going to be 0.4 over 1.3. And I'm doing all the working out here just so you can see the process. And that means that 0.308 equals e to the power of minus lambda t. If you then take the natural logs of these, you end up with minus 1.179 equals minus lambda t. And of course, our minuses will disappear, and our t is equal to 1.179 divided by our lambda, which we said was 4.33 times 10 to the minus 4 per year. So our t is going to end up being in years, and that is 2,722 years. Remember, this is a byproduct of fertilizer production, and so it is not going to be reaching its safe value of activity for nearly 3,000 years.